So in this video we want to introduce the properties of cross products, and these properties are important for a couple different reasons. One, they help us to derive practical results and establish some practical theorems, and two, some of these properties can be used to minimize computation. So they're good things to jot down in the notes, and then when you're doing calculations involving cross products, you want to identify points at which implementing these properties can simplify the work that you need to do. So right here, the first property is U cross V is the opposite of V cross U. So in other words, if you change the order of the cross, you get the opposite result. This is this distributive property for cross products over vector addition. So it says U cross V plus W. It's identifying that you can distribute the cross product over the addition sign, so U cross V plus U cross W. This one's very practical. This says, hey, if I have a scalar times a cross product, I can do the scalar times a vector first and then take the cross product. I can take the scalar times V and then do the cross product. The practical significance of this, and this is actually a very practical property. So if you're going to calculate the cross product of two vectors, like 2, 4, 8, and you want to cross that with the vector, let's say 3, 9, and 12, what this property lets you do is look to see if there are common factors. So like we could pull a factor of 2 out of this vector and leave a 1, 2, 4. And we would be crossing this with we could factor a 3 out of this one, a 1, 3, 4. And this property actually lets you do the 3 times 2 is 6, and then take the cross product of the smaller vectors. So it has a very practical application when you're working on cross products. I tend, when I have a cross product, to look to see if I have a scalar that can be factored out, so that when I'm doing the cross product, I get to work with smaller numbers. This property just says, hey, if you take the cross product of any vector with a 0 vector, you get the 0 vector, which is kind of what you would expect if you think about the definition of a cross product. U cross U is always going to give you the 0 vector as well. And then the practical implication of this is that what the extension that we can get from this is that the cross product of any two parallel vectors will always be 0. So if you can eyeball two vectors, let's say we have the vector, let's make a simple example, 1, 1, 1, and then we have the vector 2, 2, 2, and then we know they're parallel because the one vector is just a scalar multiple of the other. And so the idea is, because of the property right here, if we can, when two vectors are parallel, they must be a scalar multiple of each other. So then if you can pull that scalar out, you could then use this property to pull the scalar out all the way front, and then you would be just taking the cross product of the same vector, 2 times U cross U, which would give you 0. So when you have two vectors and you're going to take a cross product, it makes some sense to eyeball them and see if they are parallel or not, because if they're parallel, you don't need to do any computation. You just utilize this property to identify that you're going to get the 0 vector. Here is another not so obvious property. The dot product of U with the cross product of V and W can also be gotten by taking U cross V and then dotting the result with W. So this one isn't as, I think some of these are a little more obvious than others. This one is probably the least obvious property of all. As budding mathematicians, when you see claims, when you see things being claimed, like properties, for example, your mind should always go to ask the question, why is it true? So math isn't about using properties, it's about thinking about why they work, about deriving new properties, proving things. So each of those properties on the previous screen, here's property 1, can be pretty easily justified with just doing a little bit of grindy algebra. So like if we wanted to prove this, or maybe not formally prove it, but just satisfy our own desire to know why it's true, then you just do it and then try to manipulate the one into the other. Verify that this is an identity, kind of like you did in trig. You picked a side, you tried to manipulate it to make sure you got the other side coming out of it. So, like justifying this one, you would just take ijk and you'd go ahead and do u cross v. So you'd put your u vector in, and then you'd put your v vector in, and then you would take the cross product. It's going to be I times, we cross the row and column to go with I, and then we do u2 v3 and minus u3 v2, so minus u3 v2, and then it would be minus j, and then it would be cross this column and this row, so we'd get u1 times v3, u1 v3 minus u3 times v1 plus, move to the k, cross this column and row, so it'd be u1 times v2, so we get u1 v2 minus, we did u2 v1, so minus u2 v1. And then you start manipulating. You say, hey, I wonder what the opposite of this looks like. And to do that, you just pull a negative out. Pop, there it is. And if we pull a negative out, all that's going to do is reverse the order of each of these subtractions. So you reverse the order of the subtractions, and then at the same time we could use the commutative property to commute the products of these real numbers that are the vector components. So I could write it as v2 times u3, this coming up front because I pulled the negation out, minus, and then change this is going to be v3 u2 minus j times v1 u3 minus v2 u1 plus, and then it would be k times v1 u2 minus v2 u1. And then what you want to notice at that step is, hey, this looks like an ijk, and then what do we get? This is v2 times, this is a v2, this would be a v2 times u3 minus v3 minus u2, and then this one we would be crossing the j and the k, so we'd be getting v1 times u3 minus v3 times u1, and then you verify, does this go with the last piece, cross those two out, you would get v1 u2 minus v2 u1. So indeed u cross v is the opposite of what we would get if we did v cross u, because this right here by itself without the negation is v cross u. So I'm not going to prove the rest of them or justify the rest of them, but I'll probably put at least one of them in the homework and ask you to justify or verify that it works. Maybe not super formally, but step through some process where you show the one side is the same as the other.